god, that was awesome! Ah! Ah! So, Mr. Krause has lost his mind. I think so. Let's do some bonus questions, but first we have to get some coffee. So a little extra review. For those of you that are here, congratulations. You are the good students. The other kids, not so much. Anyway, let's get going. I want to be here all day. I got stuff to do. Gotta get to the hockey game. Gotta watch my boy Brendan work. Better score some goals tonight, Howell. Anyway, Yo-Yo wants to buy a car for $40,000. He's managed to save $3,000 for a down payment. He wants to make sure he loan for 6 years at 2.5% annual interest rate. Determine his monthly payment. Okay, we're going to use this formula. So, I've got a $40,000 loan, but a $3,000 down payment. So, my value here is going to be $37,000. I'm not taking a loan out for the whole 40 G's. You see what I mean? Yo. So we'll say equals. I don't know what my reoccurring monthly payment's going to be, so I'll just put R. 1 minus 1 plus I. Now, I is 0.025. Monthly payments, that means I'm going to divide by 12. Now, same thing's going to be true on the bottom, 0.025 divided by 12. But I need to raise this to a certain exponent. Now, let's see what we got. We got 6 years, and we're doing it monthly. So if I take 6 and multiply by 12, I get 72 months. So I come over to my calculator. I said, okay, calculator, put in negative 72. Why negative? Because the problem says negative. All right, so come over to the old Taschenrechner. Put this in. Oh, I got to go to calculator. Calculator. 1. Oh, control division. 1 minus parenthesis 1 plus control division 0.025 over 12. Now notice I'm just going to come outside this one set of parentheses here, raised to the negative 72 all over control division 0.025. Oops, forgot the 0.025 over 12. And I hit enter. Screwed something up, kids. Oh, what's this up here? See, that number didn't make any sense. You'll see why in a minute. Hope some of you saw this. Sometimes things don't go as planned. 0.025. And I hit enter. 66.79. So I get 37,000 equals my reoccurring payment times 66. Now again, you want to show all your work. 79570 2704 270 something like that. Okay. So then I divide by this 66.79570 Hey, looks like Mavericks work. Whatever. 66.295 and I find out my reoccurring payment is so 37,000 divided by, I might want to put 1,000 in there, divided by, now I can always just hit control answer and it'll give me this thing right here, which is what I want, and $553.93. $553.93. I think that's what it was. 92.7, but that's 93. All right, so that's what it would cost me. By the way, if I'd gotten that 480, 37,000, and I just numbly just went divided by 480, I'd find out, oh, wait, hold on, I need that as a decimal. My car payments are $77 a month. You ain't buying a $40,000 vehicle and have car payments of $77 a month. Ain't gonna happen, kids. Nope. So Yo-Yo realized after the car dealer worked his magic that this was way too expensive. His budget will only allow him to have payments of $425. What is the highest price car that he can afford? Now, believe it or not, this is sort of a tricky question, so let's see what we got. We don't know in this case what the car is going to cost. Let's call it, I don't know, cost. Whatever variable they used up there, it doesn't matter. We know that we want our payment to be $425. Oh, and I probably should put on here all the other parameters are going to stay the same. So we're going to have the same number of months and so on. So it's 1 plus 0.025 over 12 raised to the negative 72. Now, the cool thing is I can come back to my calculator, type this in, hopefully if I put these parentheses in, there you go, and then I go back and I say, hey, I'm going to take that whole thing and all I'm going to do is multiply by 425. I get $28,388, so my cost can be $28,388.17. Now this is actually not the answer to the question. This is how much money he can afford to loan or take out a loan for, because that would give him a monthly payment of $425. Don't forget, he still had the $3,000 down payment. So I take this, I add $3,000, and I say, oh, he really could have taken a loan out for $31,388.17. So that's actually the answer to the question. All right, that's one. I'll be back for the next one. So, Dr. D, Dr. Dozier, the Dr. Meister, the Doctor of Darkness, has invented a bouncy ball that actually bounces higher than it started. What? That's crazy. In fact, the ball bounces 9% higher each time it bounces. She'll drop the ball starting at 8 feet in the air. So, use a recursive rule that can be used to generate the series of heights of the ball. Recursive. So the thing you have to remember about recursion is you're going to need two lines. One is your start point. And then the second one is your formula, or your sequence. So what we're going to do is we're going to give it a start point. Now, this is pretty easy. A sub 1 equals 8. I should actually use a sub 0. It doesn't matter. I wouldn't care. 8. There you go. Woo! That was the hard part. A sub n. Now, if you remember, your recursion always uses the previous term. Where did my marker go? The previous term. So this is equal to. Now, how am I going to represent 9% higher? Well, that's exponential growth, which means it's going to be 1 plus 0.09. Or in other words, 1.09 times the previous term, a sub n minus 1. There you go. That's a recursive definition. Now let's write an explicit rule. This doesn't mean you get to swear, kids. No, that's not it. Nice try. Really, really nice try. So we're going to write an explicit rule that says a sub n is equal to 8 times 1.09, in this case, to the n minus 1. Now, why n minus 1? Because when I... Oh, wait, hold on. This would just be to the n. Why would it be just to the n? Because on my 0th bounce, it's 8 feet. So when I plug in 0, it will be 8 feet. When I plug in n equals 1, right, I want that to be first bounce. So at 8 times 1.09 to the 1th power would be a little bit more than, it would be 8.72 or something like that. So anyway, now let's answer this last part. Using either one of these rules, and I'm going to use this exponential rule. The other one's a pain in the neck. Determine how many dances will it take to reach twice its height. So, what is twice its height? Twice its height is going in there, and twice its height would be, in this case, 16, is equal to 8 times 1.09 to the n. Okay. Next step. Get the weird thing alone. Divide by 8. Divide by 8. I get 2 equals 1.09 to the n. Now, in order to solve an exponential, you have to use logarithms. So what we're going to do is we're going to log the base, 1.09. These two things will switch because logarithms are equal to exponents. So log 2.0 is equal to n. I grab my calculator. And I'm going to go log base 2. Oops. Base 1.09. Ah, you son of a so-and-so and such. Log 1.09 of... Why is that doing that? Why do you hate me? I got to do it with my mouse. Sorry. Control log 1.09 of 2. So it'll take 8.04 bounces. So n equals 8.04 bounces. Now, let me ask you this question, kiddies. At 8 bounces, was it 16 feet in the air? No, it was, so it was like 15 feet 9 inches. So at 8 bounces, I don't quite make it to 16 feet. Just a little bit off. So it will actually take n equals 9 bounces to get over. That's why I said at least twice its height. It'll take at least 9 bounces to get there. All right, I'm going to take a break and get that thing in my calculator. Okay, so we can talk about this one. Forgot to take a break. I am taking a break. All right, kids, let's drink up to this question because it's a lot of fun. Mrs. Lang has been studying the effects of annoying Mr. Krause and his increase in blood pressure. The data collected below shows the number of times she did something in class, X, something annoying in class, X, and the increase in his blood pressure. Write a model based on the given data, rounding all values to the hundredths place. So I don't know if this is logarithmic, if this is exponential, if this is linear, I don't know. So the first thing, obviously, we have to do is get the data in the calculator. So I did that. I got the data in the calculator. I've checked it. I got my X values. I got my Y values. I typed them in. But I don't know if this is exponential, if this is linear. I don't know what it is. Is it logarithmic? So I'm going to click on this doc. And I'm going to go into Insert, Data and Statistics. Down here, I'll click on X. That doesn't help us. We got to click on Y. And we say, oh, as expected, exponential growth. The more times she annoys me, the higher my blood pressure gets. Okay. So we know it's exponential. So now we can go back to this tab. We'll click on this tab over here. And we'll say, okay, we're going to do exponential growth. So menu, statistics, stat calculations, come down here to exponential. Now in this unit, you'll probably be either using logarithmic or exponential. A or B, A or B, A or B. We'll go with A. X and Y. We'll click OK. So here we go. So it said round your answers to the nearest hundredths place. So, oops. Let me get a different color. Let's go with blue. So my formula is y equals, please don't forget the y. That's so distressing to me when you forget that. A equals B equals, let me get those down, 6.23237. 6.23237. I know that's well past what I need to round to. B equals 1.12500. 1.12500. All right, so y equals 6.23 to the, or 1.13 to the x. So there's my model. That's part A. Using this model, predict Mr. Krause's blood pressure if she annoyed him 27 times. That would be like average. I'd say about average. So that's easy. You just do y equals 6.23, 1.13 to the 27. I go into my calculator. I go into calculator mode. I go 6.23 parenthesis 1.13, 1.13 parenthesis raised to the 27. And 168.89. So y equals 168.89. Now, you'll notice I asked for a really weird rounding here. I said round to the nearest 10. What? The nearest 10? That's this place. So the answer to this one is actually y equals 170. My blood pressure would be 170. Yes, I know it's 170 over 20 or whatever like that. should have said my systolic or diastolic rate. I understand the difference between the two peoples. So now down here. So y, let's copy over our equation. Y equals 6.23, 1.13 to the x. Now it says, the rest of the nice kids are worried about Mr. Krause. And realize that his blood pressure, if his blood pressure increases to 250, he will no longer be with us. How many annoyances would kill him? Such a morbid thought. I need coffee when it's this morbid. So we got to figure out when my blood pressure will get to 250. All right, it's pretty simple. It's an exponential function. In order to solve an exponential function, you must turn it into a log function. My God, my phone's blowing up. Divide by 6.23. And I'm just going to leave it like that. I don't really need it. So now I have a logarithmic function. I have, this is gone. So I have this base and exponent. So it's log base 1.13 of 250 over 6.23 equals x. Now, 250, that's a lot more than that. It's like way up here somewhere. So we got to figure out, well, I don't know. 27 got me to 170. Maybe it's going to be pretty close to that. So let's go over to the calculator. Maybe we expect 33, 34, something like that. So control, oh, here we go. I got to use my calculator, my mouse. Control log 1.13 of control division 250 over 6.23. And it should be around 30. 30.2. I probably didn't tell you how many round. I guess you can't have a half of an ounce. Let's just say I said round to the nearest number of annoyances. So the answer is 30. There it is. All right, kids. Only a couple. The best. Ms. Huff, who just happened to turn just 17, had a grandmother, a rich grandmother, who gave her $18,000 so that she could invest it. So she got 18 grand. She's going to invest it semi-annually, 2% interest, in the Nunez National Bank. Now, being that she trusted Nunez, not so much, she asked for the formula. And we need to create the model, and we're going to write that model below representing exactly how her money is going to be calculated. So we're going to do y equals 18,000, 1 plus 0.029, and we're doing this semi-annually. So it's compounding semi-annually times 2 to the 2t. That's it. That's all she wrote. 18,000, interest rate, compounding semi-annually. That's 2, and the 2 goes in both these places. All right. So how much money will she have if she doesn't touch it when she retires at age 60? So we start with the 18,000. We do 1 plus 0.029 over 2 to the 2 times. Now we got to figure out what the time is. Now if you're just a straight up crazy tool, what you're going to do is put a 60 in here. But it's not 60 years. She's not investing it for 60 years. She stops at 60. When did she start? She started when she was 17 and she got the money. So really she's going to have that money in the investment for 43 years. And I think I was playing around with some numbers, so let's see what I got. Let's just do this. All right, so we're going to take 18,000, parenthesis, 1 plus control division 0.029 over 2 raised to the 2 times 43, or you can just write 86 in there. She's going to have $79.60. Now, in what year would she have $50,000? Well, it's not going to be quite 43 years, is it? So we want to start out with $50,000. She has $18,000. 1 plus 0.029 to the 2 over 2t. So notice, I need to solve this for t. That's an exponential. In order to solve an exponential, I'm going to have to turn this into a log. So I'm going to divide by 18,000. So I don't need these zeros here. So I have 50 over 18. So this is gone. So now I've got this base to an exponent. So now I want to solve it. So log base 1 plus 0.029 over 2 of 50 over 18 is equal to 2t. Well, to finish it, I'm going to end up dividing by 2. So let's see what we got. So log, control log, 1 plus control division, 0.0029 over 2 of control division. Wasn't this 50 over 18? 50 over 18. Enter. So I get 70.96. But remember, so I have, this is really equal to 70.96, but I got to divide by 2 to get that final answer. So divided by 2. So 35.48. So y equals 35.48 years. Is that what it asked? In how many years? No, it said in what year? Oh, okay. So Mrs. Huff just turned 17. It's the year 2017. So if I take the year 2017 and I add it to this, I get the year 2052 and some little bit. But it happened in 2052. So the answer to this question is 2052. So, those of you that look at problems like this and go, oh, well, say, what? You know, answer yourself this question. If you had 3 to the 2x equals 3 to the 10, the bases are the same. If this was a 10, wouldn't they be equal? Or in other words, if this was equal to this, wouldn't they be equal? Yeah, so what we got to do is we got to make the bases the same. So I told you to try to either use 2, 3, or 5. Those are the ones that come up the most. Sometimes others come up, but those come up the most. So what I'm going to do is I'm just going to copy stuff over. 2/3 x squared, because I like putting things in parentheses, you know that. Minus 5 over 3 equals to the 9x over 7. All right, so let's see what we got. 8 is really 2 cubed. And 28, 128. Now, if you don't know this, you just come over to your calculator. Right? 2 raised to the 5th. Nope. 2 raised to the 6th. Nope. 2 raised to the 7th. Yep. Oh, there it is. 2 to the 7th. So 2 to the 7th. Now, once you have these bases the same, all you got to do is set the exponents equal to each other. Now, be careful. You got to bring this with it. Otherwise, you're just going back to the original and setting these equal, and that's useless. So you set that equal. So it's 3 times 2/3 x squared minus 5/3 is equal to 7 times 9x over 7. Okay. Distribute. 3 times 2/3 is 2x squared. 3 times 5/3 is minus 5. Equals, the 7's here just cancel and end up with 9x. So this is 2x squared minus 9x minus 5 equals 0. I bring it up here. Let's do some factoring on it. 2x and x. My guess is it's going to be, hopefully you got this, minus 5 and plus 1. So my two answers are x equals -1/2 and x equals 5. I would check them. I believe both those work. All right. Last little bit of, ooh, this one sounds crazy. I don't have to say anything. You know what I'm going to say. Ooh, forgot to drink first. The population of honeybees are currently growing every year by an outstanding 3.81%. By the way, we need bees to pollinate things, so you actually need bees. The study today shows, completed by the Brianna, how do you say that? Brianna. This person right here. Brianna, I know. Brianna bee counters told us that in the year 2016, there were only 1.2 million honeybees. in existence. Use the equation below to solve the problem. Where P of 0 represents the number of bees in millions, R is the yearly growth rate, and T represents the time in years. So, Mr. Manavongnis wants to know how many bees there will be in the year 2020. Well, it's 2016. That's just 4 years from now. All right, so we're going to go P of 4, right? Not P of 2020. It's only 4 years. Is equal to 1.2 million E to the, oh, there's a tricky part of this one. All right, so what's my growth rate again? 3.8, so 0.0381 times 4. So yeah, I kind of was nasty on this one. 1.2 E, not E, E to the 0.0381 times 4. Enter. So P of 4 is equal to 1.39755 119,241 bees. But I said round the answer to the nearest 1,000. Well, what? I only have one. I didn't say thousandths. And you think, oh, let me round to this number. No, I didn't say, oh, not that one. This one. This will be the thousandths place. I didn't say thousandths place. I said the nearest 1,000. Huh? It's only 1 point something. So here's the trick, kids. You got to remember, this is in millions of bees. And I said round to the nearest 1,000. So I got to take this thing and multiply it by 1 million. And there's my answer, 1,397,000. So really, I'm just going to move this over 6 places. So it's 1,397,551. But I said round it to the nearest thousands. So that's, now I'm like, oh, thousands place, that's this one. Oh, okay. So my answer is 1,398,000. Nasty. Sorry. That was a tough one. Dr. Brookie wants to know when there will be 2 million bees. Help! All right, so let's go back to the equation. So now we're going to put 2 in here equals 1.2 e to the 0.0381. Is that right? Times t. Because we're looking for t in this case. All right, get the weird thing alone. We're going to divide by 1.2. And I don't need to put this in my calculator. I'm just going to put it like that. So now what I have is 2 over 1.2 equals e to the 0.0381 t. This is an exponential, and in order to solve an exponential, you must use logarithms. But this is e, so now I have to use the natural log. Now, natural log base e, remember, you're not going to be able to put that in. It's just understood. It's understood to be there. It's not going to be allowed to put it in the calculator. So of what? Well, okay, these two things switch. Of 2 over 1.2 equals 0.0381 t. Well, I'm going to put this in my calculator because it's kind of nasty. So let's go. The natural log of a fraction, which is 1.2. Oh, no, it wasn't a 2. 2 divided by, doggone it, 1.2. Enter. So that's what I get, but don't I have to divide this by 0.0381? So that's what I'm going to do now, divided by 0.0381. Enter. 13.407. So t equals 13.40749. So I got to figure out, did they ask me to round the number of years? Did they ask me what year is it going to be? We got to ask. When will there be 2 million bees? When? So you could actually answer this in 2 different ways. In 13.4, in approximately 13.4 years, there will be 2 million bees. Or you could say it's, what year are we in right now? 2016. So you take that and you add 2016. And you say in the year 2029. Or you could say in the year 2029, there will be about 2 million bees. All right, kids, if you can do those, great. If you can't do those, keep studying. All right, that's the little extra for you. I hope you did it. Bye, kids.